floor is yours. Merci, Christophe. So, well, thank you all for being here today. It's kind of a pleasure to come back to the old tradition that we had, coffee and pastries and so on. Sorry for those that are remotely connected. No pastries for you. So please help yourself if you want to go, even during my talk to grab some other, pastries, go ahead. And also you can interrupt me anytime to ask me questions. Don't wait until the end to ask questions if something is not clear, okay? So as Christophe said, my expertise is in computational engineering of porous materials, okay? And I would say that my name is quite well suited for such a kind of application. For those of you who are not French speaking, vide, okay, in French, with the E, means void, okay? So I have two voids in my name, okay? So it's kind of porous name, okay? And then recently, what I realized is that not only I have voids in my name, I can reformulate my name and put valid instead. So I'm kind of meant for working in validation of porous materials. So this is what I'm going to be talking about today. So first, I'd like to acknowledge, the things I'm going to be presenting here today is not only my work; it's the work of many people. And these are a list of contributors to this work, particularly Igor Belot, who was the PhD students that worked on this project, then François Bertrand, and our collaborators at Umicore, a company I will touch upon, mention later. So Martin Botsmeyer and Robert Greiner. We're working also on this project with Bob Hayes at University of Alberta. And then we also add, a contribution in this work, and particularly in the validation part of this work, with Ishin Son, who is online, I guess, today, and Philippe Cos and François Trochu. So Philippe Cos is now at ETS, but used to be at Polytechnique. So they have contributed to this validation work I'm going to be showing. And also, I'd like to thank Christophe for, helping me translating some of the slides, and also for arranging this seminar or this workshop today, and also France Caron and Jean-Yves Trépanier, who has also prepared some of the materials that you will see in the next few slides. So this is a bit the outline I have planned for today. It's kind of, I'm going to talk about many things. They are more or less all related to the same topic, which are porous materials and validation. So first, we're going to talk about verification and validation within the modeling cycle. I'm not sure every one of you is familiar with this modeling cycle that France Caron has been working on for the past few years within the GPS program. Okay, so I will touch upon that. Then after that, I'm going to be presenting you the modeling we have done with Igor, or I would say Igor has done, okay, about three-way catalyst gasoline particulate filters, okay? And this will help me introduce basically, at the third point, the validation that we have done so far in this context. So I'm going to give you a validation case study, particularly on the flow parts of this work. So if we start with verification and validation, so let's start first to say that if you look at the axis of excellence in research at Polytechnique Montreal, so there are three main axes, and one of them is modeling, okay, modélisation en français, in French. So modeling is quite an important part of the activities of engineers. And of course, if we talk about modeling, then we need also to verify and validate that this modeling is accurate. Okay, so it is very important to touch upon these parts. And as you may know, recently, actually thanks to the GPS program, we have been implementing here at Polytechnique a verification and validation course that has been taking place for the past 4 years. It was initially given by Jean-Yves Trépanier, who retired, and then I have recently took over this course. Okay, so some of the material that I will be presenting today are taken from this course. So verification and validation is very important. And you may know this famous quote from the statistician George Box, okay, who basically said, essentially, all models are wrong, but some are useful. Okay? And I do appreciate this quote, okay, because why are they wrong? Okay? They are wrong because they are always based on approximation and assumptions. Okay? So in fact, they are never the actual reality. Okay? So there are always a discrepancy between the model and the actual reality, but it is not because the model necessarily is wrong that it is not useful. Okay? But the problem is, okay, are we doomed to be wrong? Well, there are tools to help us decide whether the model we are actually using is completely wrong, okay, or is wrong but useful. Okay? So this is a bit what verification and validation is dealing with. So the modeling cycle is quite overwhelming, as you can see here, but I like it very much. Well, if you haven't taken the time to read it, I encourage you to go. It is on the GPS website. Only the French version, and stuff is there yet for the time being. So but maybe we can post the English version. So it's very nice to look at this graph. Okay, I will show some simplified version of this chart. And so it's called the modeling cycle. I tend to prefer to see it as a roadmap to the numerical model. Okay, and so we will let you read this one. Okay, unfortunately, the next one I'm going to be presenting are in French. Okay, but I will more or less, take you through this graph. Okay? So the first part. So this is kind of simplified. I have an even more simplified version that I'm going to show you after that. Okay? But the first part of the modeling cycle basically is the relation to the reality. Okay? So basically, when you start with the problem, while you are facing a situation, and then from this situation, you have some goals that you want to achieve, or knowledge that you want to gather, or interest. Okay? So the first step, okay, is to structurize your problem and then eventually simplify it. Okay? As we said, we cannot resolve all systems, in a detailed manner so that we can, completely predict the behavior of any system, on the face of this earth. So after having structurized your problem and simplify it, well, you might be using principles or law to basically try to connect to a problem, okay? And then the mathematization of this problem. Okay? So there might be existing models that you can use, but you see that from this part is relation to reality, because in relation to the structuration, eventually you're going to be collecting data that will help you build basically your simplification. And in the end, we're going to use those data for eventually validating the numerical model. Okay? So if we move to the right, then the next step is really the mathematization. Okay? That's really take the principle and the laws that exist, the existing models, and then you put, your problem into equations. Okay? I'm going to give you later in the slides, I'm going to be showing you for the gasoline particulate filters. I'm going to try to put some box here telling you, okay, this part of the problem is this part. It is, for example, the mathematization. So if we move to the right, then we have the third part of this modeling cycle, which is the algorithmization of the problem. Okay, so once you have the mathematical equations, well, there is no computer that can solve a mathematical problem without having, come up with a numerical scheme to actually solve it. Okay? So you need to go through a step of algorithmization and eventually using numerical methods to crack the mathematical problem. And then one important part of this algorithmization will be the verification of the numerical algorithm that you will have built. You need to verify that the solution, the numerical solution you're getting is actually the solution of the mathematical problem that you're trying to solve. And then the last step is once you have your algorithm, and then eventually you crunch numbers, okay, you put it on the computer and you do simulations. Then eventually you get, certain fields like velocity field, pressure field, concentration field, or temperature. And often they are not sufficient to answer the question that you are looking for. Okay? So sometimes you need to do some integration of those fields to get meaningful data. And this is the post-processing part, okay? Which you will integrate the fields and get eventually some synthetic representation of some results that you are looking for. For example, the drag on an airfoil, the permeability for a porous media, and so on. So these are, I'm coming back here to the overall English version of this modeling cycle. Why we call it modeling cycles, because eventually you will see there are two important parts of these cycles. Okay? So the verification part that just touched upon, okay, and then the validation part that is here, okay, which is in relation to the reality, the problem that you're actually looking at. Okay? And then the validation will determine whether your model, or should determine whether your model is appropriate for the intended use for which you built this model. Okay? And depending on these results, eventually you will need to cycle. Okay? So for example, if you realize that at the validation stage that no, it is not up to the level, okay, the uncertainty related or the error made by this model are too high, then eventually you will need to go back to the drawing board. Okay? So eventually we considered some of the simplification and then redesign your problem. Okay? So this is why we call it modeling cycle. It does not need to be a cycle. Okay? If at the first validation you're like, yeah, everything is working, so you may be satisfied with the current model, but eventually if you're not, it might come back to in a loop to try to improve your model. So this is a more simplified version of the modeling cycle. So you see from reality, you come back to a conceptual model, which is basically the mathematical model. Then you do some programming, and then you get some numerical model or computerized model. And then eventually you need to verify this model, that this actual numerical model is solving the mathematical model is supposed to solve. So this is the verification phase. And then eventually, once the code is verified, then you will need to validate the whole model. The whole model is the mathematical and the numerical model will need to be compared with reality, and then you check whether you have an agreement or not. So these are just illustration of what I just said. And just to summarize, although I think I have a slide with the definition, basically, verification aims at answering this question. Am I solving the model right? Okay. Whereas validation is trying to answer this question, am I solving the right model? Okay. So I think you can appreciate the distinction between the two. Okay. So is the numerical model solving the mathematical model? Okay. And is the combination of numerical and the mathematical model getting the reality of it? So this slide is basically the same here in words, and these are definitions. But let me maybe underline two important things. Often we talk about verification and validation, but actually there are two steps in the verification step. Okay, we have first the code verification, okay, which is aiming at trying to find if you have bugs in your code, okay. So most of the time, what you will do a grid independent study or convergence analysis, as you may call it. And so you will check, your scheme is supposed to converge at a certain order. Is my code converging at this order? If the answer is yes, so it's probably the proof that you have not any remaining bugs in your code, although you need to do a lot of verification tests for all the components of your modeling to be sure that it's solving everything correctly. A step that is often overseen or not well appreciated is the solution verification. Okay? So this verification is not aiming at checking if the code is correct, is aiming at determining the uncertainty of the simulation that you have done. Okay, can you put a number? Okay, I'm getting the given permeability. At which level this permeability is correct? Is it at plus or minus 2%? So is it at plus or minus 20 or plus at minus 100%? Okay. So solution verification is aiming at determining the numerical uncertainty of the solution. And then validation, we touched upon that already. Okay. So today I won't talk too much about verification. Okay. I will touch more about validation and what we have done with Vidal in terms of validation and basically the sequence of steps that you have to do when you do validation. Of course, before doing validation, you need to verify your codes. I mean, there is no interest in trying to validate the code before having verified that there is no bug. Okay, so you verify the code. Once it's verified, then eventually you may gather experimental data. So go in the lab or eventually ask others to go in the lab for you and do the experiments. And so you gather data points. Then starts the solution verification. The solution verification will give you the uncertainty, the numerical uncertainty about your predictions using your simulation. You will need to do input data uncertainty propagation. Eventually, the model has inputs. Okay? All those inputs are not necessarily constant. Okay? Eventually, in the real life, those inputs could vary. For example, I don't know, you have a system with a given flow rate. The flow rate is, for example, 10 cubic meters per second. Does not mean that in reality, it will always stay at 10 cubic meters per second. Okay? So eventually it will fluctuate. And then you need to take into account this fluctuation when you do your validation. Okay? And I'm going to show you some examples later on. Okay? Once you get basically the numerical uncertainty and then the input uncertainty, having also the experimental data uncertainty, then you can estimate the model error. Okay, which we'll touch upon that a bit later. Okay. So enough theory. Okay. Let's go now to the modeling itself. Okay. Before going to eventually the validation of some part of this model. So we were approached by a company called Umicore. That was interested in basically understanding better what they were doing. Okay? And this company, does anyone know Umicore company? It's a Belgian company, and we worked with the research center in Germany. This is a precious metal company. Okay? So basically, they are into gold, platinum, rhodium, palladium. And one of their activities, because they have many activities, is actually to deposit catalysts, so platinum group metals, okay, into catalytic converters. Okay. And the problem is that, well, of course, as you know, all engineers are trying to improve or optimize their process. So I'm going to show you exactly what was their question in the next slide. Okay. But first, let me introduce what is a an exhaust gas after treatment system. Okay? So after the engine, usually what you have is that you have a catalytic converter. Okay? And for gasoline, you have a what we call a three-way catalyst. Okay? So basically, it's a mixture of three catalysts. And then it is meant for, of course, converting the noxious gas, such as NOx, CO, or unburned hydrocarbons. And then after that, you have the particulate filters, okay, which is meant for collecting the soot particles. But for the past 10 years, okay, there's been a trend, and it's still there. Okay, people, the OEM are still doing that. They're actually trying to merge the two units. Okay, so they're trying to deposit the catalysts within the particulate filters. Basically, for several reasons, okay? And the motivations are reduce the total number of units, reduce the packaging complexity, better remove the small soot particles, and eventually lower the overall system cost. Okay? So Umicore was particularly interested in looking into the deposition of these platinum group metals into what I'm calling here GPF, and GPF stands for gasoline particulate filter. So if I come back to the modeling cycle, I was telling you before, this is the situation. The situation is we have this device, okay, and eventually we need to optimize it. Okay. So better understanding the system basically requires a multi-scale approach. Okay? Because if you look at the catalytic particulate filter, it's kind of honeycomb structure, you see here. And then what you do actually is you're pushing the air through inside those channels here that you see here in cross section, and there is each channel as a dead end. Okay, so you're forcing the flow of air to go through this porous material here that is, for example, it could be made of ceramics, and most of them are made of ceramics. It could be also silicon carbide. And so the pore size is so small that you are collecting into this structure the soot particles. And if you have also deposited the catalyst inside, you can at the same time convert the noxious gas. So in the end, you have the large scale of the unit. You have the scale of the honeycomb structure and the channels here. And then you have what is happening inside the porous wall here. Most of the operation is taking place at this very small scale. Okay? So we have had collaboration with the University of Alberta that have done simulation, at this scale, using our own data to account for the permeability of the porous media here. And eventually we will look at this scale too. And in Igor's project, we were interested at looking at the very small scale, so the porous wall. Okay? So you need to appreciate here the dimension. Okay? This wall here is around 300 microns. Okay? So I think it's 3 times basically the diameter of a hair. Okay? So it's very small. Okay? Average pore size is around 25 microns. Okay? So 1/4 of a human hair. So the question, okay, from Umicore was this one. Okay? What is the optimal catalyst amount and the best profile to be deposited into this wall, into this porous wall? Okay? The reason is that they're having a process currently, or they had a process that was depositing, catalyst, but non-uniformly. Okay, so of course, intuitively, everyone will think, okay, probably uniform catalyst deposition will be better. Okay, so intuitively, you could work on that to try to improve your process to make it uniform. But of course, this requires a lot of money to change the process, okay, of manufacturing or depositing this what we call wash coat. Okay? It's called the catalyst that we deposit inside is called the wash coat. Okay? And because it's in form of slurry, and the slurry is pushed within the structure, and deposited after the withdrawal of the fluid phase. Okay? So you may go wanting to know, is it worthwhile investing, I don't know, tens of millions of dollars, okay, to improve a process if the gain of depositing a uniform profile is limited? Okay? So they wanted to know how much of a gain we can do if we improve the process. So, and basically what you're looking at, okay, in terms of catalyst deposition, you want a deposition that will give you the lowest pressure drop as possible, because low pressure drop means lower gas consumption and or higher power for your engine. Okay? While you want to eventually increase the capture of soot and have a very good, catalytic conversion of the noxious gas. So if I come back here to the modeling cycle, basically here the objective is the ball, okay? And then the problem is decreasing, trying to get the lowest pressure drop as possible, higher soot capture efficiency, and higher catalyst coating effectiveness. Well, just for your information, okay? I don't know if you know, but there is a big market on stealing catalytic converters. Okay? A catalytic converter is worth these days around $1,000. I even know in the countryside where I go often, there are people that have cut themselves their own catalytic converter to resell it. The reason is that if you cut your catalytic converter, of course you're polluting, of course, but you reduce the gas consumption. So we're making money on both sides, basically. But of course, the detrimental impact of the environment. Okay? And one of the reasons why those catalytic converters are very expensive is all the catalysts that are used. So it's a platinum complex metal group, okay? And it's made usually of rhodium, platinum, and palladium. Okay? So the actual recipe is not, of course, disclosed by Umicore. And you see the price of rhodium 4 or 5 years ago, it was around $1,700 an ounce. Okay, it's now $17,000 an ounce. Okay, so it's actually kind of 10 times more expensive than gold. Okay, it's actually, I think rhodium is probably the most expensive metal on the face of this earth, if I'm not mistaken. And the price of palladium and platinum are a bit lower, but there are a lot of rhodium that is used as a catalyst usually in such kind of application. So you see the interest behind all these kits are trying to cut the cost and trying to get better efficiency or performance of your catalytic particle features. Okay? So again, to come back to the modeling cycle, you saw that in the modeling cycle there was a part called simplification. So to build your model, you have to write down a lot of simplification. I have to admit, and probably you will do the same, okay? When we build a model, sometimes we take some simplification for granted, okay? And we just realize them afterwards. Okay? Actually, most of the simplification I wrote them after building the model. I said, okay, the model we built basically, oh yeah, we assume that the soot particles are quite dilute, okay, so they are not interacting between each other. So you have all kinds of simplification basically that you really need to state. Okay, normally you should start from those, okay, when you build your model. Okay? And why you need to state them is because, well, if you need to do a cycle, okay, and then rework your modeling, well, you have to revise all those assumptions, and maybe you will understand that one of them is incorrect. Okay? So here I have stated the assumption that I could deduce from what we proposed, okay? And there are many others are not written here, okay? Eventually. So to answer the question of Umicore, basically we built with Igor a four-step numerical methodology for the prediction of the three-way catalysts gasoline particulate filter performance. So it's basically there are four steps. Okay, the first step is the reconstruction of the porous wall using computed tomography images. Okay, so to get actual structures or actual structures or even simulated structures, and I'm going to show you in the next few slides. Okay? Then the second step is to compute the flow field through this porous structure using the lattice-Boltzmann method. From that, eventually you get the pressure drop or the permeability. The third step is to do to compute the capture efficiency of the subparticles. So basically, to do that, you need to compute the aerosol trajectories and eventual capture through inside the porous wall. And for that, I'm going to show it to you in the next slide. In the next slides, we solve what we call a Langevin equation problem, and we can get from that the capture efficiency. And then adding the two, adding pressure drop and capture efficiency, then you can get what we call the filter quality factor. And then the first step is the conversion. You need to convert eventually the noxious gas, and you want eventually to compute the subspecies concentration field that is transported through the porous wall and eventually diffusing and being and reacting, at the catalytic phase. Okay. So from those simulation, we wanted to get as information the catalytic coating effectiveness. So for the first step, what we basically did, as I mentioned, so the first step basically, if I come back to the modeling cycle, is basically the geometrization of the problem. Okay. So to do that, well, basically we took SEM images at 1.25 micron resolution, and then to prepare those imaging, you need to do several image processing operations such as filtering, thresholding to thresholds the different materials. Here are three materials. You have the porous space, air, you have the ceramic, and then you have the catalyst. Okay? So there are three phases to be thresholded and to be able to image them properly. And eventually you will get stack of 2D images that will be able to reconstruct your structure in 3D. So what we wanted to do with Igor is basically we have one CT scan image with one non-uniform catalyst deposition. Okay? And from that, we wanted to recreate artificial deposition, either uniform or either non-uniform, and then test them to see whether they would be better or not. So from this out here, it's only a 2D cross section, just to illustrate. So you see, you have in white, you have the catalyst phase. In black, you have the pore space, and in gray, you have the substrate, which is the ceramic, the cornerite ceramic. So initially, it was a non-uniform distribution profile. From this non-uniform distribution profile, we were able to recreate with some algorithm that we developed different non-uniform profile. Okay, so you see here, basically we have eroded the catalyst space so that we have changed the non-uniformity of the distribution, and we have changed the amount of catalyst that is in the structure. Okay? But by playing with the catalyst layer, we can put even more non-uniform catalysts to increase the amount of catalyst within the pore structure. We generated 9 structures at different coat weight and different distribution or non-uniform distribution. And what we can do also is completely remove the catalyst from the original image and then redistribute it uniformly. Okay? So you see a different level, different cost weight. So which is having four uniform distributions. So here I just put all the images next to each other, okay, just to illustrate a bit the process. The original image is this one. So you see that you have lessened basically the non-uniformity or reduced the amount of catalyst here. Here there is frigates, still non-uniformly. And here we made it uniform. And eventually here the two cases are the extreme cases, which are the bare porous wall where there is no catalyst at all. Here, so I told you these were 2D cross sections. Eventually, we do our calculation in 3D. So these are the actual, some of the actual, structure that we have generated. So this was for the first step, which is the reconstruction of the first wall at different, catalyst amounts. Okay. Then eventually, you need to compute the flow field using the lattice-Boltzmann method. So this is one step of the mathematization process. Okay. So lattice-Boltzmann, I won't go into details. I guess most of the people here in this classroom, I think, have heard about lattice-Boltzmann, and I taught some class where we talked about lattice-Boltzmann. Just for those of you who are not familiar with lattice-Boltzmann, basically, instead of solving the Navier-Stokes equation, okay, we are actually solving the Boltzmann equation, which is a mesoscopic representation of the gas or fluids. Okay, and we're solving for F here, which is the probability distribution functions of finding molecules of the gas or the fluid going in a certain direction. Okay? But by doing so, we are able actually to recover in the end. If we integrate those probability distribution functions, we're able to integrate them and recover the velocity field that is usually given by solving the Navier-Stokes equation. Okay? The advantage of this approach is that the LBM explicit scheme is very simple to implement on the computer. And it's very local in terms of parallelization. It's a very local scheme. You only need the information of the neighboring nodes so that you can parallelize this code or this scheme pretty easily on parallel computers and then resolve a very large system. So this was the second step, so the lattice-Boltzmann. The third step, we solve the Langevin equation. Okay. What is the Langevin? So it's also, what I'm going to show you now, it's also part of the mathematization of the problem. Langevin's equation is basically a stochastic differential equation. Okay, so it's actually Newton's second law of motion that we're solving for each soot particle. So we launch eventually 100,000 of soot particles. We calculate the trajectories, and when those soot particles hit a wall, they are supposed to be captured by electrostatic forces. And so they are influenced by the drag, but they are influenced also by Brownian diffusion. Okay? And the Brownian diffusion term is the stochastic term. Okay? So you can see here, actually, you see that the blue trajectories here. So the first material here is over here. Okay? So here, this is the inlet section. And you see that the blue trajectories here are quite erratic. It's because they are mainly governed by Brownian diffusion, and eventually the ones that are able to go deeper into the structure. So the structure, you cannot see the structure is transparent, but the trajectories that goes, deeper in the structure eventually are not so much influenced by Brownian diffusion. Okay. So we solve this equation to determine the trajectory and the capture of the particles. And by doing so, the procedures allows to account for the main capture mechanism for filtration. So that is interception of the particles. You have inertial impaction, and you have Brownian diffusion, which are the three main mechanisms for capturing very small particles in this size range here. So eventually, we do that, a lot of computation. Okay, and the last and not the least is now the catalytic conversion. Okay, so eventually we'll need to solve advection diffusion reaction equation. Okay, per species that we want to solve. Okay, so with Igor we only looked at one species, but eventually with Mobin that is at the back here, we'll try to look at more species at the same time. And we do this also with the lattice-Boltzmann equation. So another mathematization. Basically, I told you that lattice-Boltzmann is a CFD solver, but actually it's more than a CFD solver. It's a partial differential equation solver. So you can devise it in such a way that you can actually resolve an advection diffusion reaction problem. Okay, and recover using the Boltzmann scheme, slightly changed. Okay, you can recover your continuum mechanics equation. So this gives you some of the results here for the flow field. So you see a structure. So again, the first wall is 300 microns, 3 times the diameter of the hair. And then you see why you have the catalyst, the chondrite, and the pore space, and then we simulate the flow through the structure. And such kind of simulation using LDN takes around 2 hours. What she used to take, because I think this was done probably 5 years ago. I think now probably down to probably 1 hour, okay, of computation to simulate that using 100 pores. Another snapshot of the flow fields. So you see here for uniform distribution, this is the flow field that we get. For a non-uniform one, this is the flow field, and eventually we solve also for the concentration field. So basically, this, if you look at the modeling cycle, this is the solution part of the modeling cycle. So just a few snapshots of the result that we gathered. Okay, the idea, I recall you, was to determine, is it worthwhile investing a lot of money into a process that will, make the deposition more uniform? Okay? So using those simulations or this modeling, basically we were able to get what we call the quality factor, and the quality factor is simply the ratio of the capture efficiency, E, divided by the pressure drop. Okay, so the higher the quality factor, the better the material is filtering. Okay. And look at the impact of the catalyst deposition on this filtration. Okay? So here, fraction of pore volume field means that the more you go to the right, okay, the more catalyst you put into the bare porous wall. Okay? So in green, you see this is for the non-uniform distribution. In red, this is for the uniform distribution, and you see that if you want to deposit a certain amount of catalyst within the pore space, eventually you can determine how much improvements you can get in filtration efficiency, going from a non-uniform profile to a uniform one. Okay, so there are, I don't remember exactly, there's 30% improvements in the filtration performance. On the other hand, here you see the graph for catalytic conversion of a species, which could be, for example, CO. And then again, you can also determine, going from a non-uniform profile, how much improvement in conversion I can get if I go to the uniform one, and it was about 20%. So after that, this is not my decision to decide whether they should invest on the new process. Okay, they have the data, and now they need to decide whether it is worthwhile to do it. So basically, this is, if you look at the modeling cycle, this is the graphical representation of the results that you get in the post-processing. Very interesting here. Very interesting results. I can tell you the story. I know I told the story to some of you, like Mobin, but I like the story. That's why I'm telling you the story. So one day, Igor comes to me with these results. Okay, this was one day before going to Germany and present the result to Unicor. And then what you see here, so we fill the pore space with catalysts here. And this is the capture efficiency of the particles, of the soot particles. Okay? And then I look at the red line and say, yes, this is exactly what I expect. You put more and more catalysts into the pore space. So you kind of plug in the pore space. So the efficiency of capturing the soot should be higher. It's increasing, okay? As I would expect. Okay? And then the non-uniform profile is getting that. Is decreasing. To me, this was very counterintuitive. So I said to Igor, are you sure you didn't make any mistakes? He said, yeah, why? I said, because I'm not waiting. I was not expecting such kind of result. I was expecting, eventually a monotonic increase also of the capture efficiency when you were clogging with the catalyst, even though it was a non-uniform profile. Okay? So he said, no, I'm sure this is a good result. Okay? Said, do you have an explanation? He said, no, I don't have an explanation. Okay, so we go to Germany, okay, present the results, and then I said to Igor before the meeting, I said, either they find us very stupid to show this graph, okay, or either this is what they're actually seen in the lab. Okay? So we present the results, and then Martin Votsmeyer has smile, and then myself, I'm saying to myself, is it he finds us stupid, or is it he has already seen that? And after a few seconds, he said, this is very good. This is exactly what we have seen in the lab, but we don't know why. And he told to us, and you do know why? No, we don't. We don't, but we will, because we have all the data. This is what is nice with numerical modeling, is that you have the details of the flow field and everything, so you can try to understand what's really happening. And after after 1 or 2 weeks of plotting some of the simulation and trying to see, you see here what you're seeing is two uniform profile, okay, at 2 different cut weights. Okay, so this one is a low cut weight, this one is a high cut weight. Same thing here, non-uniform distribution now. Low cut weight, high cut weight. Okay? And what you see is that, so I'm highlighting in yellow here the same zone. Okay? You see here, basically, if you look at the blue flow field, okay, it's kind of more or less the same, despite the fact that we have increased the amount of cut weight. Basically, there are kind of the same numbers of channels going through this section. Okay? For the non-uniform profile, yeah, same kind of channel here and here. Okay? But for the higher cut weight, which was around here, okay, somehow the numbers of channels has completely decreased. Okay? And the reason is that we deposit non-uniformly the cut weights, so it is clogging preferentially the small pores. And the small pores are the most efficient to capture soot. Okay? So the more we were putting non-uniform deposition of catalysts, the more it was clogging the structure in such a way that the small pores were gone, and we were only left with big capillaries that were not so much efficient in capturing the soot. So what's happening is that your capture efficiency is decreasing, but after some point, you're putting so much catalyst that eventually your large pores that remains, well, they will start to decrease in size, and then they will come to the efficiency of the small pore in the end, and then your capture efficiency will increase again. And eventually, if we go higher, you will reach probably the same level. So I think this was very interesting to see, how we can, from numerical modeling, get information that the experimentalists were not able to understand. So basically, if you look at the modeling cycle, this is interpretation. Now, to talk about the last part of the talk, to give my last part of the talk, I will probably go a bit faster, although it's probably the most relevant in terms of validation. This is one of the graphs that we got, okay? Permeability. Okay? So variation of permeability as we fill in the pore space with catalysts, permeability of the uniform profile. and here the green probability of non-uniform profile. Okay? And then we say, well, we need to try to validate this. Okay? But remember, those crosswalk are only 100 microns thick. Okay? I have computers in my lab, okay? But I have no bench, no lab, no instruments, and nothing okay, to do experiments. Okay? So a challenging goal is, well, we need to find a way to validate this without having money and without having resources. Okay? So we came up with, I think, a nice approach here, which I will show you now. Okay? So can we validate this result? Okay? So here we're just showing you the validation of the flow part of the modeling. Okay? The other part of the modeling, it's still ongoing work. Okay? So we thought initially at doing, well, using basically, can we have the digitized structure, okay, from CT scan. Okay? We have generated, fictitious, structures, but we can use a 3D printer and print them, but at the magnified scale. Okay? So it happens that at the same time, I went to visit François Trochu's lab and Ishun and also Philippe Kors, and they showed me a parameter that they had, okay, of this diameter. Okay? And then I thought that, well, maybe we can print those structures at different coat weights, and then put that in the parameter, and then measure permeability and do just simply dimensionless analysis to try to get experimental data. Okay? The thing is that if you look at the literature, so far people were not so much successful. Those guys in 2019, not very conclusive. This one had an error of 1 order of magnitude. Okay? This one was a bit better. It was at 30% error, but it was using stereolithography, which was very expensive. And I said to go, we need to do that with a fused filament 3D printer, the most basic 3D printer. So this is what we did. Okay, so from the digitized structure, okay, we cut those samples bronze, okay, and then we send them to the printer. We magnify them at a certain scale. Okay, I'll give you some idea about how to choose the right scale in the next few slides. Okay, then you see I taken the right color because I have many of them of different colors. I can pass them on if you want. Okay. Like to do so. These are the colors of different coat weights. So you print them, and then after that we will put them in the parameter, okay? And the parameter is simply a column, okay, in which silicon oil is passing, okay? And we're collecting the silicon oil at the bottom of the parameter, and then we measure the evolution of the silicon oil collected over time, so the mass. And from that, we can reconstruct basically, get the permeability of this sample. Of course, this sample is magnified, so we need to take into account the magnification of the sample. But we can get experimental data, and then after that we can compare those dimensionless experimental data to numerical data. Sorry. So I'm going to go very fast now. Okay, the scaling process was not done, randomly. Okay, we basically used, kinematic similarities. Okay, we used four criteria to decide what should be the scaling factor. Okay, so the first one, we try to stay the same flow regime. Okay, so this gave us as information that the scaling factor should be around 103. Okay, based on the silicon oil we decided to use. Okay. Of course, we could have changed eventually the properties of the silicon oil to change this factor here. Okay. Then the second criteria was did the printer add a sufficient resolution, okay, to print the small poles that we wanted to print, okay? So from this, we come up with a criterion that was telling us that the scaling factor should be much greater than 4. Okay? So the other scaling factor is what we call the Brinkman screen length, okay, that tell us that if you have the elementary representative volume of your porous media, the size, the S here, the size of your sample should be much greater than the square root of the permeability that you're trying to measure. So you came up with this here scaling factor needs to be much smaller than 40,000. And then the last one was the permeameter sensitivity. Of course, the permeameter, it has its own sensitivity, can measure permeability on a certain range. So eventually, this led us, after some algebraic calculation, that the scaling factor should be between 6 and 140. So in the end, if you put all the scaling factor on the same scale, we came up with, luckily, okay, of course, we could have changed that by changing the silicon oil properties. Eventually, we could have changed the scaling factor. But basically, we came up with this range. And then, of course, we chose the one that was the simpler to deal with, which was a scaling factor of 100. So then from the image, STL image, from the CT scan image, you can make STL files. You can, using Cura, you can print them, using this printer here at Polyfab. And then you can make different samples, the ones that are circulating, okay, at different coat weight and different porosity. Then you can check if the porosity of the printed samples are correct with regard to the digitized structure. And then we found that there was a good correlation between the fake one and the real one. And then you put the samples into this permeameter that issued Philippe Koss and François Trochu at Vidal. So you see, we put our sample here, we put silicon oil, and then we drain, and then collect over time the silicon oil. And this is much simpler and less much costly than actually trying to measure the pressure drops to very small wafer of the 300 microns, original porous material. And this can be built from home improvement store materials. So I'm passing you the detail. You need a baseline, so the calibration, and then eventually you need to solve for the height of the liquid into the column, and then the only unknown will be the permeability, and then you can recover the permeability by integrating this equation. Passing you the details. So eventually we came up with this graph here. Okay, so you see, I've replotted the graph. This is the same graph I showed you a bit earlier. The only thing is that now the scale here is semi-log. Okay? So you see here, you see the behavior of the uniform profile here. You see the non-uniform profile, and you see the gray data here. The light gray are for the non-uniform magnified twins, as I call them. Okay, so you see that we are kind of reproducing the trend. Okay, and those ones here are for the uniform profiles. Okay? Again, it seems that we are quite reproducing the right trend. Okay? And here the error bars are a standard deviation of the reported mean values. Because we have not simulated through only one structure. Okay? When we do simulation, we simulate through several pieces of those porous walls. So eventually we get numerical uncertainty due to the input data, the input structure that we use. So the question that I recently got, that I asked myself, okay, based on the materials that I'm teaching, the verification and validation class, okay, is that good enough? Okay? Is it a good model? Okay, and in the verification and validation class, okay, we actually show a few methods to determine whether the error of your model is small or large. First, let me show you what you see in the literature. Okay, when people are trying to do validation, okay, a lot of time what you see, well, people show a field, I don't know, stress field or velocity field, and then they compare experiment and computation. So usually comparison is kind of not too bad, but not too conclusive. Okay. Some people they vary the input data. Okay. And then they get some response for the simulation. This is the line here. And then they get experimental data around the line. So gives information better than the flow field, but it's still not so much conclusive to me. Then if you're lucky, people put experimental uncertainty on the experimental data, so you get error bars that tell you be better whether okay, this is a good agreement or not. Okay. Then eventually they include numerical errors. Okay, so the uncertainty also on the simulation. So then I'm getting better. Okay. Yeah, you can better appreciate now the adequacy of the model. And some people also, they do include also the uncertainty on the input data. Eventually, here the post structure of each simulation we have done was slightly different. Okay, the porosity was a bit different. So eventually, here you may have a variation related to for example, in our case, it was the amount of catalyst put into the structure. It was varying from one structure to another to a certain extent. Okay. So basically, the graph I showed you right before, okay, on the results, basically we're more or less this graph, okay, where we have error bars, okay, for the experimental data and the numerical data, but can we do better? Okay? And then if you follow the verification and validation class, okay, the answer is yes, you can do better. Okay? And what is this better? Well, this is computing the error of the model. Okay. So computing this kind of work, which I'm going to show you in the next slide. Okay? So taking the data from Igor. Okay? So this is basically following the procedure from these standards here that are here. So if you want to have a look at it after the class, after the workshop, feel free. So there exist some standards since 2009, okay, to tell you how to precisely validate numerical models and to be able to determine the error of your model. Okay? In the end, to determine whether your model is adequate or is not. Okay? So basically, if you read the standards, it's going to tell you that there are several error source of errors. Okay? Basically, you have the experimental errors. You have the errors related to the variability of the inputs. Okay, it's called delta inputs. You have the errors related to the numerical scheme. So usually this is the discretization error. Okay? And then eventually you have the error of the model. Okay? What is the error of the model? Is the error due to the assumption that you have taken. And basically this SME standards tells you how to determine the error of your models. So what we will need to compute is this. So a simple convergence analysis will help you to determine what we call the grid convergence index, which will give you this value. You can do uncertainty propagation of the input data. You can get relatively easy this value. Eventually, experimental errors are given to you by the experimentalist. And what you just need to compute now is the E, which is the result of your simulation minus the result of the experiments. Okay? So in my case, it's, for example, permeability of the simulation minus permeability of the magnified samples that we have created. Okay? Of course, scale at the right scale. Okay? So I'm going a bit faster here now. So basically, in the end, what you can get, okay, you can get the error of the model here, and you can get a uncertainty range about the error of this model, which will be equal to the difference between your experiments, your simulation and your experiments, plus or minus k times the overall uncertainty that is defined here. So the model uncertainty, which is equal to the uncertainty due to the variability of the input data, numerical uncertainty, and experimental uncertainty. And the K here gives you the confidence interval levels that you are interested in. So if you want 95% confidence interval, you can take K equal to 1.96, and then you get 95% confidence interval. So you can do, this is the procedure is summarized here. I'm going to pass that very quickly. So the convergence analysis, we've done that a long time ago for lattice Boltzmann. We know it's converging to a higher degree than 2. You can get what is called the grid convergence index. Okay, I'm not going into details now, but this grid convergence index can tell you what is the uncertainty about your numerical data, numerical scheme. You can get also U inputs, so the uncertainty related to the variability of your input data. In this case, the variability of the structure I'm providing to my simulator. Okay, I won't go into detail of this graph. And here I'm getting to this graph here. Okay, that gives you here delta model, which is the error of the model, which is the error based on the assumption that you have taken. So in theory, if a model is good, a perfect model will give you points. Here, as you see, I have a few points here, which has the comparison between simulation and experiments. If the model will be perfect, all the points will be on the 0 here line, okay? Because this is the difference between simulation and experiments. Okay? And eventually, the uncertainty, the best model will have is 0 uncertainty. Okay? That would be the best case scenario. Okay? Here, what we see, well, all the data points are not on the 0 line. Okay? They are actually kind of following a trend, as you can see here. But what we see is that the uncertainty due to the numerical scheme, to the experimental data, and to the input data, basically is very large, because permeability is a very sensitive material property. So what you're looking for in this case, when you cannot reach 0 here, is that your uncertainty bars, they cross the 0 line. Okay? If the uncertainty bars crosses the 0 line, you can deduce that your model is not so bad, okay? Because you are within the uncertainty, the different uncertainties that you have in your model. Okay? So you see for the uniform distribution, we're getting error bars almost crossing all the time the 0 line here, except for this one. And actually, you see that there is a trend here. There is a trend. Why? It's because if we go back to the permeability, of course, the permeability is changing quite significantly. Okay? So these are absolute values. Okay? So eventually, what you need to do is to normalize those values, okay, to have something that is more consistent to what you're looking for. Okay? And here, if you do that, this is the graph that you're getting. So this is the error of the model, the relative error of the model. Okay? So what you see is that most data points basically are having kind of 20% discrepancy between the simulation and the experiments, but all the uncertainties bars basically are crossing the 0 line, except for this point. Okay? This point eventually is the scenario that you are not looking for. Okay? That is, you have discrepancy, but the uncertainty bar is not crossing the 0 line. Okay? But overall, I think we can conclude that this model is actually quite good because of the very large variability of the natural variability of permeability that we can see here on the uncertainty part. So I'm going to stop here my talk. Okay. Well, summary is quite obvious. A novel validation procedure has been devised. I showed it to you with this permeameter and then printing magnified, twins of the structures. Okay. We have applied that to gasoline particulate filters for once successfully, I believe. The impact of the Washcott distribution and amount of permeability is well recovered. And the model error, at least for the fluid parts, is within experimental and numerical uncertainties. And I think I have convinced you that V and V standards are great tools to determine model adequacy and assess its predictive capability. I didn't have time to talk about predictive capability, but if you are interested, well, there is again a course given on verification and validation, and I invite you to take this course next year if you're interested. Okay. So I'm going to stop here. I have another slide to show you what are our plans, but I think I have taken too much time. You have some reference textbooks if you are interested. This is the Bible, okay, of verification and validation, or the Quran, depending on what is your religion. Okay, so this is here the book, and there are some standards, as you can see here. Okay, standards for verification and validation in computational fluid dynamics and heat transfer. I have it here if you want to have a look at it. And as I said, there is a class related to this topic, so I invite you to follow this class. So thank you for your attention. If you need more information about this verification and validation work, you can go to Igor's articles and scan here the QR code will link you to this page. Okay, so thank you for your attention. And if you have any question, please feel free.